So we're down to stacks and queues, having done lists, and they're very important data structures, especially stacks, where I did decide to add a stack buffer overflow project to this class, which I'll demonstrate probably on Wednesday, maybe later today, which is a little complicated, but it does show you what the real point of these things is in practice. And so stacks serve a real important purpose. The primary purpose of stacks is so functions can call subroutines, and they can call further subroutines and further subroutines. And must say, I learned to do this manually. I was a research scientist in physics and biology and stuff for many years, and then I got a job at a financial company running databases. And I'd never worked under these conditions. I was handling hundreds of millions of dollars, and I was working on complicated mathematical calculations on this money, and then the phone would ring, and there'd be an emergency, and a client would need me to drop it and do something else, and then the boss would come in with a more important emergency, and have to run off and do with that, and then I would come back to my desk hours later. This stuff has to be done by 5, and I don't even remember what I'm doing. So I learned to keep notes, and this is what your hard drive does now. Now, in the days of Windows 95 and Windows 98, hard drives worked this way, so if your operating system crashed, it would just forget what it was doing and have no record. So when it booted back up, it would find these files copied onto the disk partially and would not know what they were. And it would just spend time sweeping them up into files called file 000 and file 001. And then the operating system developed a journaling capability. And that's what I learned. I would write down everything I did on a list, so that even if I'm interrupted, I can figure out where I left off. Anyway, that's the point of this. If you think about it, if I call the main routine of my function, then I call a subroutine, then I call a subroutine of the subroutine, when I return, I have to remember where I left off in the intermediate function and where I left off in the function above it. And when I terminate that function, I have to know where to return to in the operating system above it. And that's what stacks are for. So you can only put data in on top like a pile of plates. And I don't know about the cafeterias here, but when I went to school, they had a spring-loaded plate thing. She'd shove it down. She'd only put it on top. You can't even reach the bottom, and you can only take it off the top. And this is perfect for a stack. Your operating system is way down here at the bottom. Then you launch the program. Then the program calls a subroutine, another subroutine, until you're 7 or 8 layers deep. And when you return from this one, you return to that one, return to that one, return to that one. You can find your way back home if all those stack frames are intact. So push puts something on the end, pop takes something off the end, and peek reads from the end, although I've never used peek, not in this context. So the top pointer points to the top of it. This is called the stack pointer in processors. In modern Intel processors, it's called the RSP. There was a whole series of names as we went from 8, 16, 32, and now 64-bit processors. But the stack, that points to the top of the current stack frame. And all right, so you can create a stack. You can push things onto the stack. You can examine them with peek, and you can pop them off the stack. And if you pop them off the stack, they come off in reverse order. So if you push on eggs, and then you push on ham, now when you pop, you're going to get the egg first, and then the ham later. So, all right. So this is your book's diagram to explain the concept I was telling you. You're running a program, then you make this one. You're running a program, then you call function B, and so you enter. You start down here at A. Okay, this is Python. So you start down here at A. You enter A when you run the program. Then A is apparently intended to call B, although I'm afraid, there's the source code. Okay, B up here, I'm C. No, I don't. All right, here, that calls A. Now I'm catching on. Okay, this is the main routine. Then it calls A, which you see here. Then A calls B, which you see here. And now, when you return, you have to return them in opposite order. You have to return from B to A, then return from A to the calling program. They're showing it to you in Python. All right. So you can implement this with an array. Now, if you do that, it's going to have fixed lengths like we talked about before. Arrays are efficient, but you define them at compile time, and you're stuck with that size. If you make a list, you have variable length, but they're less efficient. So if it's implemented with an array, you might not be able to push because the array is full. You only have room for 3 items. You try to push again, it's just going to give you a stack overflow. This, by the way, is the harmless kind of stack overflow. Yeah?
Real quick, so if we save the stack as an array, that just tells us the max amount of elements we can have, not the minimum.
Right. It's just maximum. You can have less, of course, yeah. It reserves all this space. And so it's got all that, but it only has that much room. So when you try to push another one, you have an error. Now he's calling it a stack overflow here, which is possibly one word for it, although that word is typically reserved in security context for a stack overflow when you push an element that is too large onto the array and it leaks into the next element's space, which we'll talk about. But anyway, that is certainly one form of an error. All right, and so that's how push works. The array is initialized here. This is what initializes it. You determine the size and it creates room for that many numbers, and that's it. So you only have room for 3 if size is 3, and so if you call push more than 3 times, it's going to give you a stack overflow. All right, so you push onto the stack, push eggs, ham, spam, and then when you push new and new 2, then you're going to get stack overflow. Only 3 of them will fit, the rest will not fit. And when you pop things, you take them off the top and then delete it, so the pointer moves down here. The stack now only has 2 items, now it only has 1 item, now it has 0, and if you try to pop again, you got an underflow. You tried to pop off an empty stack. So it's the opposite of the overflow. So that's simple enough for a data structure. And there's the underflow happening. Pop 3 times. The 4th time you pop, you get warned with an error message that there was no data to give you. All right, peek will just show you what's on the stack, and that, of course, will work unless the stack is empty. Then it will say there is nothing to peek. All right, now you can do it with a linked list, which is more appropriate if your stack is going to grow at runtime and perhaps shrink. So you just push in data by adding another node to the end. You pop out data by removing this node from the end. And here's the pointer to none at the end of the stack. So it's very, very similar, and similar to what we've done before with linked lists. The only thing is, of course, you'll never get error that you can't push any more things on unless you actually run out of memory, which is not likely in a modern operating system that has virtual memory. And but the pop, you could still pop too many times and run out of information. So, all right. Now the node class isn't quite right for this. It looks like this. What you want, if you push in data, you'll add it here and make a pointer there. So the top will move over here. And you have a pointer pointing to what used to be the top. And so inserting an item onto an empty stack looks like this. This is push, so you create a new node, and then if you're at the top, then you make your node point to the top and make an S, otherwise you just add it to the existing one. So I think this is the one that makes a new stack with just 1 item, and this is the one that adds to an existing list. So you can make a stack of 3 elements. You push egg, ham, and spam, and then you print them. They come off in reverse order, like I said. Now, the reason why they don't recommend this is because the while loop reaches into the node class, which I think I'm seeing here, current.next. You actually refer to the internal features of the node, and that is considered a poor way to design something, because you want to encapsulate all the details of inside the stack, so all you see is push and pop from the outside. This is abstraction, which is a real important concept, and it underlies everything we do. Like the normal user just sees a screen and they move their mouse around and click. They are unaware of the fact that there are all these assembly language instructions and network trackers going on behind. And so you really don't want somebody who wants to think about a stack having to think about the pointers, current and next. That's detail should be taken care of by the library. So here's a pop element. You pop this off, so you just move the top pointer over to here. That'll delete that one from the stack. And so if you pop on a stack with only 1 element, then you just set the pointer to none. That's going to make it an empty stack, where all you have is a pointer to none, no actual data. So that's fine. All right. And I've got the code for that, but I don't think it's necessary to demonstrate it. I think it'd be more fun to do it with a real stack. And there's peek. Peek is incredibly simple. You just return the data inside there. Let me check and see if there's people with questions in the Twitch. And there are not. Okay, good. All right, so one application of a stack is bracket matching. This is one way to do it. If you have expressions with open and closed brackets and curly braces and such, you can push them onto the stack when you have opening brackets and then pop them off when you have closing brackets. and then make sure they match. That's one possible way to implement a parser. And you've got some homework projects where you implement a parser. I didn't do it that way, but that is one way you can do it. Now, the homework problem you only had one kind of parentheses, and so what I did was just find the rightmost opening parentheses, because then I know there's nothing but a closing parentheses after it. But in general, taking human typed input and having to parse it is one of the most dangerous things on computers, and this kind of thing frequently fails. You can very often trick things that take input from humans with unexpected characters that cause it to do something it shouldn't do. So here's an example with a whole lot of braces, and so as you go, it's going to test, going to push it on. Okay, so I think it started from the right, which is a little strange, but it's going to check brackets. Let me see if I can understand how this one works. The check brackets is going to, last is this. I guess, yes, they're pulling it from the right. You could just as well pull it from the left. But here they are. This one was a parentheses. This one was not. And I don't quite understand what they're doing here. I see, three different, I was just checking these to see if, they ran the whole thing through. They didn't show the operation. So they're checking to see if this one matches. It does match. This one apparently does not match, and this one does not match. That's the point. Okay. And I think it's because I see a curly brace opening there. But it closes there? No, that's all right. Yeah, I don't see why. I see these extra parentheses are what makes it fail. This one is right. This one is missing a parentheses. This one has extra parentheses. In both cases, it will fail the test. All right. And then there's queues, which is the obvious alternative to a stack where you add data and you serve people in the order they arrive, like waiting for line to go to a movie or something. You can only insert elements at the rear, and you can only take them off at the front. This is the normal, this is first in, first out, instead of first in, last out. So you call it NQ when you add a new person waiting in line, and you call it DQ when you pop somebody off the end and serve them. So you got Q and NQ, and you can measure the size, and DQ is, that's what the equivalent of pop, NQ and DQ. DQ removes someone from the line, taking the person off the front, the data element off the front. So you can do them with a list, you can do them with stacks, or you can do them with node-based linked list like we've done before. They'll all work. So list-based queues, you just define a list, and then the front and the rear are both 0 and the size is 3. This will create a class of list as the initialization. It makes an empty list. And so NQ is going to add data here, and another NQ will add data there and data there. So here's the code that does it. If the queue is not full, self size equals self rear. Okay, so this looks like it's actually done with an array, I would think, although it looks like a list. I don't understand. They set a size limit arbitrarily. They set a size limit of 3. I don't know why you do that, but they did set a size limit of 3, so this notices if it's full. Other than that, you just append the data to the list and move the rear over. So you can push on 20, 30, 40, and 50, and here they are. 20, 30, and 40 go on. 50 will not go on because it's full. All right, and so when you DQ, you're going to take them off the head. So this one, 3 will go off first, then 11, then 7, and the queue will get smaller as you do that. All right, and Python's list actually has a pop method, which I've never used, but that's one way to do it. Anyway, deletes the last item from the list and returns the deleted item. So here's DQ, which they implemented with pop. So you have a list, and you pop off the item from the front end of the queue. So it's not hard to set up. You can do it with linked-based lists. So you can have lists that have a next and a previous pointer, and then you can have a queue created out of that list where you just define the head and the tail pointing to that list. And then you add a new element into an empty queue. This is going to be the data, the next pointer, and the previous pointer. Both of these point to none because there is no extra item on this way and there is no item that way. There's just a front and a tail, which both point to here. So this is a queue with only one entry. And when you add another item, then you have several steps. You assign the new data element, assign its next pointer to none, its previous pointer back to the previous of what used to be the tail, and the next tail pointing to this tail. That's what you do. And the new tail moves over here. So you add to the end. So it's pretty simple. All right. And DQ is again the same. You remove this data, and now you take these pointer that goes to the previous now goes to none. And this is now the head, the front, moves over to here. You can do it in a stack, and I found this to be quite convoluted, and I'm really not sure why you would do this. But they claim you can do this if you really need to make one of these functions much faster than the other, which is a fairly common situation in programming. I know if you use RSA encryption does multiplication and exponentiation to a very large number, and you choose a very large D for decryption and a very small E for encryption, so encryption will be fast because that takes place on your phone or something, and decryption is slow and that takes place on a powerful server. That's the idea. So sometimes you want one of these operations to be faster than the other. So if you're willing to have the DQ operation be costly, then you have two stacks. NQ uses push to add item. You have two stacks. Adds item to the first stack, so NQ is fast. And DQ involves popping elements off stack 1 and putting them on stack 2 because you can only take it off the top. And when you DQ, you have to take it off the other end. So you have to reverse the order by putting them on the other stack, then pop the element off the other stack, and then push them all back. So that does make it long and complicated. That's going to be order of n. The other one will be order of 1. So you can do that. NQ is order 1, because you just create an element and add it to the stack. DQ is order n. You have to move all n items to another stack and move all n items back, so that's 2n operations. And you can do the opposite, of course. If you want the NQ operation to be costly, then use two stacks. And NQ is what puts the data on the hidden end, so you have to push the whole stack over here, push it on, and then roll the whole stack back. But DQing then becomes cheaper. So that's all I wanted to show you. The application of these things, they say, are for a printer queue and a music playlist. Now, I may not have the cahoots for you. Someone was supposed to prepare them for me, but I'm not sure that happened. Let me see. I'm going to check and see if they have appeared. But I'm afraid my assistant did not get them ready in time today. Take a quick look and see if they are there. Hey, this is chapter 5, I think, right? This is, yeah, I don't have them. All right, so it won't be cahoots today.
So how
Yeah.
would it be used for a music playlist?
Well, music playlist, you push them in, put in 5 things, and you want it to play the first one you put in first, and then the next. That's all. It's more logical than, say, a stack. Because in most items, you probably want the last in to be the last out. First in, first out. That would be logical.
I see.
Yeah.
Modern day programming, you don't really encounter this as much, right? Because it's just for music playlists and printer.
Well, no, you encounter it everywhere. It's being used constantly. In fact, that's what I'd like to show you. Is right on target. No, this remains very important.
Okay.
Is it because it's faster?
Well, it's just essential. If you think about the structure of programming languages where you call a function, you call a subroutine, they're all written like that, and the only efficient way to do that is with a stack. So the stacks are really important. And the queues, I think, are important for these other things, for things where you do want to maintain the order and have the, I admit both are very important for different applications. Yeah. Let me check for comments online. Dead. Yeah, well, my mobile data was disabled too. That made a problem for me. All right, so I'm going to stop this recording.